Thank you very much, and I'm very happy that indoor location isn't solved yet. So I was able to do this work with my collaborators, as you can see there, from TU Darmstadt, Fraunhofer IGD, TU Dortmund, and WinLab. So the motivation of our work basically comes from my work in my previous organization, where we worked a lot on systems for elderly people, and especially systems that do indoor location. In order to do smart home automation and also save energy, for example, switch on lights when people get up from bed and go to the toilet during night. And one of the most interesting use cases also was for recognition. So as a caregiver, one has the opportunity to install an app and then get a notification when somebody falls down. And we've actually been deploying this system in 23 apartments in an elderly home in Germany. And it's a big touch screen, as you can see here. So very similar to a mobile phone, but just enormously bigger. And these electrodes that are deployed on the floor build a matrix of 20 by 20 centimeters, and sensors are being deployed near the walls. That build up an electric field to the person, and if the person falls, it measures the contact area around the person. But as you can see, the installation is quite cumbersome, and also existing apartments are hard to equip with this technology. So our research question was, are there easier ways of achieving this? Providing indoor localization and perhaps identification as a first step, and maybe as a second step later also for recognition. And we have certain requirements on such a system, which is being tag-free. We do not want to force the inhabitants of the elderly home to carry a tag while they go to toilet at night. We also want to preserve their privacy, which would rule out camera-based technologies, for example in the bathroom, and we want to lower the installation effort. And especially in this community, there have been a lot of approaches on Wi-Fi localization, Wi-Fi Doppler, FMCW, modulated radar, or even radar technologies to recognize spoken words or vital signs. But we will have a closer look at capacitive systems now, and we will see later how they are different from other systems. So when we look at the external fields around us, instead of generating our own fields, we can leverage the fields that come, for example, from appliances like power lines or lamps. And you might not notice, but you're surrounded by electric fields, because we humans don't have a sense for electric fields. It's somehow hard to imagine. Platypuses do, and that's why our system is called Platypus. And researchers have been building systems based on sensing external electric fields. For example, the top one here, where they use the power line electric field to localize a person, or the two bottom systems by Kuhn and others, who were using electromagnetic noise to detect gestures, to detect whether somebody touches a wall, for example. But all these approaches require training because our environments are somehow very unique, and also the power lines might run in different configurations. But we can also leverage another interesting fact, and that is that the human body electric potential changes during walking. And there are two reasons for that. Reason one is we accumulate charge, mainly due to charge separation. So when our soles come into contact with the floor, there's a charge separation going on, also called the triboelectric effect. And this charge basically accumulates while we walk. And there's a second effect that also comes in when we look at the human body electric potential, and that is the capacitive coupling to the environment. So as soon as I lift my foot, the capacitive coupling changes and my body voltage increases. So these two effects, the charge accumulation and the change in capacitive coupling, results in a very characteristic pattern in body voltage that can exceed up to 2 kilovolts or even more. So there's a huge electric field being emitted by a walking human, which we have not used so far. Work has been mostly focused on doing motion sensing, as the first work on the top left here, where we have a worn device that determines body motion. Rake motor analysis have developed a gamepad that uses a contact-based measurement to detect whether somebody steps or even jumps. Or Kurita and others have used this technology to detect human walking motion, mainly to look at whether people have irregularities in their walking. Our system, as I said earlier, uses the two effects here and uses a non-contact based measurement. So we deploy sensors on the ceiling. These sensors are coupled to the human person with a very, very small capacitive coupling, around 100 femtofarads. And this enables the sensor to perceive the ambient electric field around that human. The hardware looks as follows. So we basically have an electrode that builds up or perceives the electric field around us. The electrode is decoupled with a voltage follower that enables the electrode to float freely and adapt to the ambient electric potential, and an amplifier that basically gives us the final sensor value. Our hardware looks like this. So the shiny part is the electrode of the sensing IC. We use an IC that is mostly used for ECG measurements, for example in car seats, but it can also be used for this type of motion sensing, as it is very high impedance. Just to give you an example of how the sensor signals look like, this is me stepping, and with the stepping my body voltage changes and I affect the ambient electric field. So when you see me lifting my foot, you see that the signal goes down quite strongly. When I put it down back again, you can see also a body voltage change. Obviously, when I start jumping, the change is quite significant, as you can see now. So that's what we're currently measuring. Now looking at a number of sensors, we can see that when a person walks in a circle, let's say underneath the blue sensor at first, and then going around towards the black sensor, we can see that the body voltage starts to build up slowly. We have a period of charging and accumulating charge. Then there's a saturation where the charge that basically comes in flows off again, and a discharge when we stop. And we can see that as soon as we're close to a sensor, these sensor values are slightly larger than the others, and also due to the higher body voltage at the end, we'll get higher values at sensor 4. However, these results here are very, very clean results, and in the beginning when we were working with these signals, we found it very hard to understand what's actually happening. And that's why we built a predictive forward model, and this forward model is able to reconstruct the sensor output based on what the user is actually doing. So our sensor output is basically composed of some filters which determine the frequency response of the sensor, and also the capacitance between the person and the sensor and the body electric potential. So now we have two unknowns in this equation, and we need to take a closer look at the capacitive coupling between the person and the sensor. And we modeled the capacitive coupling by using, again, two unknowns, x and y position. For simplification, we assume that the z position is fixed, and we assume a fixed body height. We have a fixed maximum capacitance between the sensor, and we model the decrease in electric field by a parameter alpha. That should ideally be 2, but in our case it's 2.5, so another simplification to make this model a little less complex. Just to give you an example of how that looks like, when we look at the real sensor data, and for this sensor data we recorded the person's location and also the person's body voltage, we get these results, and our predictive forward model is able, just using these three inputs, to generate very similar sensor values as the previous one. And this enables us to inverse the model later on, and use it to determine a person's location and also a person's body voltage. So our main workflow consists of 3 steps. First is the localization. Second, and that's what's very unique about our system, is that we're actually able to determine the change in body voltage as if it was a direct contact-based measurement. And that opens a space for new activity recognition applications that could recognize changes in body voltage, for example, due to activities like touching objects, moving, sitting down, stepping, and so on. And thirdly, we identify users because we see that the body voltage is quite distinct from user to user, extract features, and identify the user based on classification. So let's first have a look at localization, mainly using the stepping amplitudes for 3 sensors and then applying multilateration. So here we can see our setup. We have 6 sensors deployed on the ceiling, a surface area of 2.5 by 2 meters. And this is an example of the localization accuracy. We actually built that live, so that system works quite well for multiple people. As you can see here, when people step out of bounds of the grid, they are being recognized near the bounds. In order to evaluate our system, we recorded data from 30 different users and 16 different walking paths per user that were randomized over this surface. We also recorded data with and without a grounded metal card to see how the influence of sensors of objects are on the localization results. As a ground truth, we recorded body voltage using a high impedance voltmeter and also the body configuration using a Kinect camera. Here you can see the localization results. We achieve a median error of 16 centimeters for 30 users. This is for normal walking. For slow walking, we get significantly smaller errors of around 13 centimeters. So just to state significance, we ran an ANOVA on this data. The great thing is that we do not require any person-dependent calibration, and also that the grounded metal card did not have an effect or a significant effect on the localization accuracy, which is great because in a living environment we will have furniture, we will have like big grounded metal armchairs and so on, so that's very positive. For the localization results, we can see that in the center, between the 2 grid cells, we get a higher error than in the middle and at the edges, for example. So let's have a look at the second step. Based on the localization, we can infer the change in body electric potential. What you can see here is basically a graph of the body electric potential, which we measured, and then the one that we reconstructed in red. And the top graph shows an error of about 6% for the estimation. We can see that our estimation doesn't have these high frequency components as the measured signal, but still it comes very close to the actual signal. On the bottom there's a bad example with an error of 16%, but that is very unlikely in our reconstruction. As you can see, the mean error is around 8.8%. Again, smaller movement speeds lead to smaller errors in this reconstruction. So when we have this body electric potential and also the localization, we can go on and identify a user. And that's using some features which we extract and then classify with a support vector machine. So the first set of features we extract is the minimum and maximum of body voltage, and also a histogram over a trajectory of about 5 seconds. Also based on the localization and these very characteristic dips you can see here, which correspond to the steps, we are able to determine the mean step length and the mean step duration, and also the mean speed a user is walking with. However, moving forward, we can see that the signal amplitudes are not quite the same, and they tend to decrease over time. So what we do is, for each step, we extract the step, normalize it, and then create a concatenated step series, which you can see here in the second picture. And based on this series, we extract some spectral components, and also again a histogram. We also overlay all the different step signatures and then compute standard deviation and the mean step signature of a person during a walking sequence. Just to give you an idea of how that looks like, we've got 30 different users. The step signatures look quite distinct from user to user, and these are some examples. Here, for example, we have a user with very, very thin soles. And we can see that also the body voltage is very small, and there's a lot of noise in the step signature. On the other hand, if we have users with a very, very big sole, we can see that the step signature is very clean. We achieve high body voltages, and when we move further, we can see that people with the same shoes achieve very similar results, so the step signatures look quite the same, and we attribute that to the materials being used in these shoes and also the style of walking that can be more distinct for running shoes, for example. In terms of accuracy, we reach 94% accuracy for identifying 4 users. For 30 users, it's about 75% accuracy. We could not see any difference between normal walking and slow walking, and a good accuracy can be reached after 3 to 4 training samples. So if we have a system, let's say in a hallway, we will need some training samples before we can actually identify or distinguish a couple of users reliably. We also showed that features persist over multiple days, which is good news. However, they change with footwear. As we can see in the bottom plot, where 3 people wore 2 different types of shoes. The middle one didn't change, the others did, and this also adds some dimension of uncertainty to these sorts of readings, which is sometimes a bit hard to explain and hard to interpret. So to conclude my talk, first of all, we carry out localization based on measuring ambient electric field changes. We achieve a median error of 16 centimeters for normal walking, 13 for short walking. We also show that the accuracy depends strongly on the speed of walking. In the future, of course, it would be great to support multiple users, which I haven't touched so far, but which would also require to deploy more sensors. Second, based on the localization, we extract the body electric potential with a mean error of 8.8% compared to direct contact-based measurements. And we think that especially this is a very interesting modality for future activity recognition systems, which has not been explored so far. And thirdly, we identify users based on their step signatures. We achieve an accuracy of 94% for 4 users and 75% for 30 users. The identification can be retained over multiple days, but changes with footwear. Again, in the future, currently we're mostly looking at change in body electric potential. We would like to actually determine the absolute body electric potential, and also get a little bit better at recognizing users with very low body voltage by basically creating our own hardware that would support different gains and analyzing that. So I thank you very much for your attention, and I'm looking forward to questions.